Newton's third law. All right, so Newton's third law states that for every force exerted by an object, there's an equal but opposite force exerted on it by another object. So if you stand on the ground, you apply a force equal to your weight, which is the force of gravity, mass times gravity, which pushes down on the ground. The ground then pushes back up on you, which is called the normal force, with the same magnitude but opposite direction. All right, so that is an example of Newton's third law. For every action, there's an equal but opposite reaction. You apply a force to the ground of your weight, or the force of gravity. The ground applies a force onto you, the normal force pushing you up. If you push your hand against the wall, you can feel the wall pushing back on your hand. All right, so you're pushing on the wall, but you feel that force pushing back up on you. Static friction. So if you try to walk on a frictionless surface, okay, so let's say you're wearing super slippery shoes and you're on slippery ice and you're trying to walk, well, what happens? Your foot slips and slides backwards and you never propel forward. In order for you to walk forward, there must be a force of static friction that pushes forward on your foot. Okay, so that relates to Newton's third law. The person pushes backwards against the ground or the earth or the ground pushes forward on the person. Okay, that's static friction. Force of action, person pushing backward against the earth. Reaction, the earth pushing forward on the person. Okay, so let's look at question 1. A person pushes a large crate across a rough floor. Draw a free body diagram of the person and the crate. Okay, so this is a free body diagram of both the person and the crate together. Okay, so we'll start by drawing a dot. Okay, so this dot is representing the person and the crate. Okay, so together, the person and the crate have a force of gravity. And it always points straight down, so let's draw that. Force of gravity pointing straight down. Okay, the person and the crate are on the surface of the ground, so there's an equal but opposite normal force pointing straight up. Okay, so now we're drawing a free body diagram of the person and of the crate separately. Okay, so we're doing the force of gravity. I'm going to say force of gravity of the person and the normal force of the person. Okay, so what's happening here? The person is pushing against the crate. Now, the person doesn't feel the force of the person pushing on the crate, because that's the force that the crate would feel. But the person feels the crate pushing back on the person. So this would be the force of the crate on the person. Crate on person. Okay, that is like the reaction force. You push against the crate pushes against you. Okay? Now, if we take a look at the crate, the free body diagram would look very similar. So we have the force of gravity of the crate. We have the normal force of the crate. But the crate is also feeling the force of the person pushing on the crate. So this would be pushing the crate forward. So this is the force of the person on the crate. Okay, notice that it's equal magnitude but opposite direction to the force of the crate on the person. All right, so now the person is also pushing against the floor, and so the floor is pushing forward on the person as well. So the person pushes against the floor and the floor pushes forward on the person. So if we had to draw a free body diagram of the floor, the floor would feel the person's push on it going backwards. So if this was the floor, it would feel a force of the person pushing back on it. And now there would be an equal but opposite push of the floor on the person. So this is the floor on the person. Okay, and that would be going forward. And it would be equal in magnitude but opposite in direction. All right, so if the person is actually accelerating forward, then we would know that the magnitude of the force of the floor on the person, so this vector here that's pointing forward, would have to be bigger than the force of the crate on the person. So this vector, the force of the crate on the person, then would have to be a bit smaller than the other one. So it'd be smaller than the force of the person, the force of the floor on the person, which propels it forward. Okay? So when we add a pulley to the problem, we can treat all objects connected as one system, or we can treat each block separately, so you can decide which method you prefer. All right, so a cord is passing through a frictionless, massless pulley, has a 4 kilogram block tied to one end of the left pulley and a 12 kilogram block tied to the other end on the right side of the pulley. So let's draw what that looks like. So here's our pulley, and we've got a rope. Here's my block. Okay, I'm just representing it as a dot. So it has a 4 kilogram block. I'm just going to write 4 kilograms here on one end, and we have a 12 kilogram block on the other end. Assuming that the blocks start at rest. So determine the distance each block will travel after 2 seconds. Okay, so the 12 kilogram block is heavier, so it's going to travel downwards, and the 4 kilogram block is lighter, so it's going to travel upwards. And the distance that the 4 kilogram block travels up will be the same distance as the 12 kilogram block travels down. So we're just trying to find that distance. It's the same distance for each block. Okay, so what we're going to do is we're going to draw a free body diagram of the system, but I like treating all the objects connected as one system. Okay, and you can do this until later on in the course when they start to tell you that the pulley itself has a mass. Okay, once that happens, see in this case the pulley is massless. We're assuming that it has no mass. So when that's the case, then we can basically just treat the pulley as though it has no mass, and we're going to treat this as one big system. Later on, when it has a mass, we're going to be doing this a little bit differently. Okay, but for now, we're going to do it this way. So as long as your question says that it's massless, then you can do it this way. So what we're going to do is we're going to treat the whole system, so this whole thing, as one big system. Okay, and so there are forces that are pulling the whole system, causing it to rotate in this direction, clockwise, and there are other forces causing it to rotate in this direction, counterclockwise. Okay, so let's think about what the forces are that are acting. So we have the force acting on the 12 kilogram object. So that would be the force of gravity. So I'm going to call this one A and this one B. So this is the force of gravity of B. And then for the 4 kilogram object, we have the force of gravity of A. Okay, now each of these objects also have a force of tension that's pulling up. So this would be force of tension A and force of tension B. Okay, but since the force of tension is inside the system, so it's included when we circled the whole system, it's included in that it's in that string there, the cord. So it's part of the system. And since the pulley does not have a mass, the force of tension A and the force of tension B are equal to each other. So they kind of cancel each other out. One is causing the whole system to rotate clockwise. The other one is causing the whole system to rotate counterclockwise. They're equal in magnitude. So they're going to cancel one another out. So we can completely disregard them right now. Okay, and right now we're doing part A. In part B, we want to find that tension, so then we're going to have to look closely at that. Okay, so for now we're doing part A. We're trying to look at, well, what is the net force that's acting on the system? When we enclose the whole thing, including the cord and the pulley and the masses, all as one system, we just see two countering forces. We have the force of gravity acting on B and the force of gravity acting on A. So I'm going to choose a direction, and I like to choose the direction that the objects are actually moving in. So in this case, since the 12 kilogram mass is heavier than the 4 kilogram mass, then this clockwise direction is the mass that the direction they're actually moving in. So I'm going to say that's my positive direction, and I'm going to say F net is equal to mass times acceleration, right? Newton's second law. So what is my F net here? So I have my FGB, which is in the positive direction because we said clockwise. In this case, we're going to assume clockwise is positive. That's the direction it's actually going. So I'm going to say FGB. And then my FGA is in the other direction, so that would be minus FGA is equal to M. And when we talk about M, what are we referring to? This is the F net equation for the whole system. So this is the mass of both of the blocks. So I'm just going to write that as MA and MB times the acceleration. So what is FGB? FGB is just the mass of B times gravity, minus FGA, which is the mass of A times gravity, equals MA plus MB times the acceleration. Okay, so we're trying to find the distance each block will travel after 2 seconds. Before we can do that, we need to solve for this acceleration here. So let's do that. The acceleration is equal to MBG minus MAG over MA plus MB. So let's plug in everything that we know. So I'll write it on the side. So we have a 4 kilogram mass on the one end on the left. So that's MA is 4 kilograms. On the right side, that's B, which is 12 kilograms. We know G is 9.81. We can plug everything in. So MB is 12 times 9.81 minus 4 times 9.81 over 12 plus 4. So I'm going to type this onto my calculator. So I have 12 times 9.81 minus 4 times 9.81 over 16, which is 4.905 meters per second squared. Okay, so I'm working on part A right now, but I'm not done. I just calculated my acceleration. All right, so we want to know the distance that the block is going to travel after 2 seconds. So I'm looking for my delta S. That's my question mark. My time is 2 seconds. And it says, assuming that the block started at rest, so that means my V initial is 0 meters per second. And we just found out that the acceleration is 4.905 meters per second squared. All right, so I'm trying to find the distance the block is going to travel. So we can use this equation. S final equals S initial plus V initial delta T plus 1/2 A delta T squared. If I bring my S initial to the left side, I get S final minus S initial, which is the same as delta S, the change in the position, equals V initial delta T plus 1/2 A delta T squared. All right, so I'm solving for delta S. My V initial is 0, my delta T is 2 plus 1/2. My A is 4.905. Delta T is 2 squared. So I can type all of this into my calculator. And I get 9.81. Delta S is a distance that's traveled, so that would be in meters. So that's A. Okay, when I move on to part B, I'm looking for the tension in the rope. To calculate the tension in the rope, I'm going to have to draw a free body diagram of one of the two objects. I'm not going to be able to draw a free body diagram of the whole system because in the whole system, the tension is within the system, so I'm not able to analyze it. I'm going to pick one of the two objects. It doesn't really matter which one I choose. In fact, I can do both of them to show that I get the exact same answer both times because we know the force of tension of B is the same as the force of tension in A. because it's the same rope. So let's draw our free body diagram. So I'm going to do this of A, FGA, and this is the force of tension acting on A. Okay, so here I have my free body diagram, and I've already said that object A is moving upwards, object B is moving downwards. So if I did my F net equation, for this object I would say up would be positive. F net equals MA. So what is my F net? My positive force is the force of tension of A. My negative force is my force of gravity since it's pointing down, equals M. This time my mass, I'm referring to the mass of object A because this is a free body diagram of A, times the acceleration, which I just found in part A. So if I'm trying to solve for force of tension A, it would equal M times A plus FGA. So my mass of object A, which is 4 kilograms, times my acceleration, which I found was 4.905 meters per second squared, plus FGA, force of gravity A, we already said the force of gravity A is just mass of A times gravity, so it would be 4 kilograms times 9.81. All right, so I'm going to type this up and find out what I get. And here I'm getting 58.86. So my force of tension is 58.86 when I look at the free body diagram for object A. If I did the same thing but looking at object B, I can do the same thing and I should hopefully get the same answer. So let's look at B. So in object B, I have a force of gravity acting downwards, and I have the force of tension acting upwards. This time, I know that object B is traveling down, so I'm going to say the positive direction is downwards this time. And I'll write F net equals MA, but I'm talking about object B. So F net for object B would be FGB is positive minus tension would be the negative direction because we said down is the positive direction. I always like choosing the positive direction to be the direction it's actually moving. The mass, we're referring to object B in our free body diagram, so it would be mass of B times the acceleration. So we should be able to solve for F tension B. We'll bring F tension B to the other side and MBA to the other side. So we'd have FGB minus MBA is equal to force of tension for B. So I'm just going to write it in the other direction. Force of tension for B is equal to FGB, which is the mass of B, 12 times gravity, minus MBA. So what's our MBA? We have the mass, which is 12, times B times A. So the mass of B is 12 times A. A is what we already found, 4.905. All right, so I'm going to type this up. 12 times 9.81 minus 12 times 4.905. And I get 58.86. So of course you only have to do this one time, but I did it both times to show that you get the same answer either way. So the force of tension is 58.86. It's the same tension whether you're looking at the tension acting on object A or object B, since it's the same rope. All right, so that's the tension in the rope. That's the answer to part B. All right, let's look at question 3. A steel block of mass 1.8 kilograms and a copper block of mass 6.3 kilograms are connected by a string over a pulley with negligible mass on top of a steel wedge-shaped ramp, which makes an angle of 30 degrees. The coefficient of kinetic friction between steel and steel is 0.570, and between copper and steel is 0.360. What is the acceleration of the copper block? All right, so again, what I can do this time, they didn't say anything about, they said that the pulley has a negligible mass. Whenever they say that, you can just assume that we can make this all one big system. It makes this problem a lot simpler than if you were to separate it. And that's the way I like to do it. So this is going to be one big system here. I'm just circling it all, and I'm just connecting it like this is all one big system. So I'm going to draw all the forces acting on the system. So for mass 1, I have a force of gravity, which is pulling down on it. I'm going to call it Fg1. And I have a normal force, Fn1. I have a tension, but that tension is inside the system. So I can call that T1, but I'm not even going to look at that tension when I do part A, asking for the acceleration, because it's part of the full system. It's within the system. There's also a tension on mass 2, T2, and that tension is equal to T1, but they're countering each other. And so they would cancel each other out anyways. Okay, we know that there is friction going on in this question, so there is going to be some friction acting on mass 1. The whole object is moving in this direction, and so mass 1 is moving to the right, meaning that the force of friction is moving to the left. The object is moving, so this would be kinetic friction, Fk1. For mass 2, we have a force of gravity pointing straight down, so Fg2. We have a normal force, but the normal force is perpendicular to the surface, so that would be in this direction. So that would be Fn2. And we have a force of kinetic friction. Kinetic friction opposes the motion of the object. The object is moving down the ramp, so kinetic friction would move up the ramp. So it looked like this, Fk2. Okay, so now we can start calculating everything that we need. So we'll start with Fg1. So Fg1, they tell us that the mass of object 1 is 1.8 kilograms. So Fg1 would be mass 1 times gravity, which is 1.8 times 9.81. I'll calculate that on my calculator. And I get 17.658 newtons. I can find the normal force, so Fn1. I know that my net force in the y direction for this object, F net y, must equal 0 because the object is not moving in the up or down direction. So the normal force and the Fg1 must cancel each other out. So I could write it out if I wanted to. F normal is positive direction, gravity is in the negative direction, so it's minus. Together they make 0. So if I solve for the normal force, it has to equal force of gravity. That makes sense. They need to cancel one another out. So my normal force would be 17.658 as well. Okay, so since I know my normal force, I can also figure out my force of kinetic friction, which equals the coefficient of friction for object 1 times the normal force of object 1. So what is my coefficient of kinetic friction? It says the coefficient of kinetic friction between steel and steel is 0.570 and between copper and steel is 0.360. Okay, so I have a steel block. This one is steel over here. And this one's copper. Okay, so for my steel block, the coefficient of kinetic friction, and it's all on a steel wedge-shaped ramp. So this whole thing is steel. Okay, so for the first object, it's steel. This is steel on steel. So it's the coefficient of friction between steel and steel is 0.570. So that's my coefficient of kinetic friction for this one. 0.570 times the normal force, 17.658. So I'm going to multiply those two, and I get 10.658 0.065 newtons. Okay, I'm going to do the same thing with object 2. So Fg2 is equal to m2g, which equals the mass of object 2, which they said in the question is 6.3 kilograms times 9.81. And I get 61.803 newtons. All right, so now I want to find the normal force over here. Okay, so to find that normal force, we know that the object is moving down the ramp here. So this is the direction the object's moving. So what we need to do here is we need to change our axes so that the direction the object is moving becomes the x-axis, and the perpendicular direction, which is the direction of the normal force, would be the y direction. So in that case, because the object is moving down the ramp in the x direction, we would say that the object is not moving, nor is it accelerating in the y direction, which means that the net force in the y direction has to be 0. So I'm going to say that positive is the direction of the normal force, and the net force in the y direction has to be 0. And I'm going to do that to figure out what my normal force is. So are all the forces acting in that y direction? I have the normal force, which is positive, so F normal 2. And then I have the component of the gravity force that is acting in the y direction, in the negative y direction. So that would be this force here. So this would be Fg2y. And then there's also, I could decompose it into Fg2 x. So my force of gravity, which is going straight down, can be decomposed into an x and y component. So if I take a look at my F net y, I have a normal force that's going in the positive direction, and I have my Fg2y, which is the force of gravity, the component of that's in the y direction. But that's going in the negative y direction, so it would be negative here. Fg2y, and that equals 0. So how do we solve for this Fg2y? Well, what we could do, I'm going to redraw this picture down here so it's a little bit more clear. So this angle, they said, is 30 degrees. Here's my force of gravity. So my force of gravity here, and then I can decompose my force of gravity into force of gravity y and force of gravity x. Okay, so this 30 degrees, where does it end up in the triangle that I just drew? So if I were to, I'm going to change my color here. So if I were to draw this triangle like this would be a 90-degree angle, this would be 60-degree angle, and this right here would be 30, because together they make 90. Okay, so the angle in here is 30 degrees. So that's what's important to know there. So if that angle is 30 degrees and I'm trying to find Fgx, so this vector right here, that's opposite of the 30 degrees. So then we would be doing hypotenuse, which is Fg, sine of 30, since it's the opposite side. Okay, so I have F normal 2 minus Fg2, which was 61.803, sine of the angle 30 degrees, equals 0. So now I can solve for F normal 2 by taking the 61.803 sine 30 to the other side, so it becomes positive, and I'm going to just type that onto my calculator. And I get 30.9015 newtons. All right, so now I know my normal force. And once I know my normal force, I can then figure out what my force of kinetic friction is for object 2. So my force of kinetic friction is the coefficient of kinetic friction for object 2 times the normal force for object 2. The question tells us that the coefficient of kinetic friction between copper and steel, which is the object 2 is made of copper and the surface below it is steel, is 0.360. So that's my coefficient of friction for object 2 times the normal force. So I'm going to multiply that on my calculator. And I get 11.125 newtons. All right, so now I have all of my forces other than the force of tension, which I said those are internal inside the system, so we don't have to worry about them right now. Okay, so what is the acceleration of the copper block? So if I take a look at the whole system now, I'm going to just erase what I have over here. So I'm continuing with part A right here. If I take a look at the whole system and I say this direction, the direction everything is moving is the positive direction, I can say F net equals MA. My F net, what would that be? My F net are all the forces that are helping the whole system move down the ramp. So what are all the forces that are making it go down the ramp? Let's see. So I've got the force of gravity that's in the x direction over here. I've got tension, which I said I'm going to disregard because T1 and T2, they cancel each other out. So Fg2 is really the only force that's helping this whole system go down the ramp. What are the forces that are pulling or resisting it from going down the ramp? It's Fk1 and Fk2. Those are the two forces that are resisting the whole system from going down the ramp. They're the forces that are trying to pull it up the ramp. Okay, so now if we look at those forces, we'd say, okay, well, F net would be Fg2, positive, because that's the force that's pulling it down the ramp, minus the other two forces, Fk1 minus Fk2. Okay, again, we could say plus T1 minus T2 if we wanted, but T1 and T2 are inside the system. They're equal in magnitude. They would have canceled each other out, so we can disregard. Equals mass. So now this mass is the mass of the whole system, because that's what my free body diagram is. So it's M1 plus M2 times A. Okay, so now A is what we're solving for. So I'm just going to rearrange. Fg2 minus force of kinetic friction acting on 1 minus force of kinetic friction acting on 2 divided by the sum of both of their masses. All right, so now we need Fg2. And really, I should have put Fg2x because really it's just the x component of Fg2, right? So it's this here, Fg2x. All right, well, Fg2x, that's the opposite direction of the, oh, I'm just noticing my Fg2y was wrong because my Fg2y is the adjacent side of 30 degrees. And I said that it was the opposite, but it's really the adjacent. So we shouldn't have been using sine all along. We should have been using cos. So let's fix that up right now. It's very easy to make little mistakes like this, so you just need to be checking your work. Okay, so I'm going to change this to be cos of 30 degrees. So FGY, as you can see here, it's adjacent to the 30 degree angle. So that's why I should have put cos. So I'm going to type that up again. 61.803 cos of 30 degrees. And I get a different answer now, so I'm just going to fix that. And that's 53.523 newtons. And now that's going to affect my FK2. So my F normal 2, I'm going to put in 53.523. And then I'm going to multiply those. It's going to change my answer. So I'm timesing it by 0.36, and I get 19.268. All right, So when I'm looking for my FG2x is opposite of the 30 degrees, so it would be FG sine 30. So FG sine 30, my FG is 61.803 because I'm talking about FG2 here. So I have 61.803 sine 30 degrees minus FK1, which we found already. FK1 was 10.065 minus FK2. FK2 is 19.268 all over the sum of both of their masses, and both of their masses was 1.8 plus 6.3. So I'm going to type all of this on my calculator. 61.803 sine 30 minus 10.065 minus 19.268 over 1.8 plus 6.3. And I get 0.194 meters per second squared because it's an acceleration. All right, so that's question 3A. 0.194. I have here 0.193. So it might be a slight rounding error, but my answer that I got on my calculator is 0.1936, so I rounded it up to 194. Okay, part B. If a spring scale were placed between the steel block and the pulley, what force would it read? So here's the pulley, and the steel block is M1. So they're saying they're putting a spring scale right here. What force would it read? So really what the question is asking is, what is the tension in this string here? Okay, so they're just asking for the tension. It's a fancy way of saying that. What force would it read? So the question is just asking, what is the tension? T1. And we already know T1 and T2 are the same value. So it doesn't matter whether we find T1 or T2. They're asking us to find what is T1. Okay, so to do that, we're going to do it much like we did question 2. We're going to draw a free body diagram of one of these two objects. So I'm going to do it of mass 1. What are the forces acting on mass 1? So we have T1 pulling to the right. We have FG1 pulling down. We have F normal 1 pulling up. And we have FK1 pulling to the left. Okay, so we already know the values of FG1, FN1, and FK1. We're looking for T1. Okay, so we're going to start with our Fnet equation. The object is moving to the right. The whole system is moving to the right and down the ramp. So I'm going to say right is positive. Fnet equals MA. So my Fnet in this case, positive direction force is T1. My negative direction force is FK1. My mass, I'm referring to mass 1 because that's what my free body diagram is of. And my A is my acceleration that I just found. So I'm solving for T1. So I'm going to bring my FK1 to the other side, make it positive, which equals my mass 1, which was 1.80, times my acceleration, which was 0.194, plus my FK1, which is 10.065. I'm going to type this all on my calculator. I get 1.8 times 0.194 plus 10.065, which is 10.4 newtons. And that's the tension in the rope, which is also the force that the spring scale would read if you placed it between the steel block and the pulley. All right, so there's 4 more questions that I'd like you to try out from this lecture, and all of the solution videos are posted in the homework section. All right, so try the next 4 questions, see if you can do it. Do them on your own, and then take a look at the solutions and see if you can follow along if you got stuck anywhere. Double check your work. All right, thanks so much.